So in our last lesson we looked at antiderivatives, which were basically the opposite of derivatives when we were working with functions. This is still in our unit on integration, and we're going to take a little bit of a different approach here in this lesson. Integration is all about finding the area under curves. This is one of the big applications of integration, is to find the area under the curve. So to get us towards integration, we're going to today look at some approximate methods of finding the area underneath the curve. Basically, how can you estimate the area underneath the curve? And looking at the techniques that we use in this section, we're going to combine them with our antiderivatives, and that should take us to integration proper. So here's the big question here. How do you find the area underneath the curve? Well, one thing that we could do if we just want to estimate the area under the curve is we could take our function here. Our function here is just y equals x squared. So this is just a parabola opening up. And if I've got my graph here, I can imagine underneath my graph, taking the area underneath the graph and dividing it into a shape that I know how to find the area of. So I can imagine dividing this thing into rectangles. Now let's say I wanted to find the area from here to, I don't know, let's say right about here. So I might take this spot and I might sort of draw some little rectangles here underneath. So I've drawn sort of 4 little rectangles. Okay. I can even label these guys 1, 2, 3, and 4. Now, how do I find the area under the curve between this point here and this point here is going to be the sum of the area of those 4 rectangles. So let's say we want to find the area from, let's say our first point here, we'll call it x0, and our last point here is going to be x4. So we want to find the area between x0 and x4. Well, we have these other little x values where our rectangles begin and end. Call them x1, x2, and x3. So what are we doing here? We are going to say that the approximate area, sorry, we're going to approximate the area under the curve using a series of rectangles. And the rectangles that I've drawn here are what we would call left endpoint rectangles. Okay. Because the left side of each of these rectangles touches my my function, y equals x squared. So the left endpoint is on the curve. Okay. Another way of describing these, so this is the left endpoint is on f at x. Okay. Another way of describing these is that these are inscribed rectangles. Okay, because they are completely under the curve. Put that on the next line. They are completely under the curve. Y equals f at x. So how exactly do we get our area here? Well, our area, let's find the area of each one of these little rectangles here. So if we want the area of rectangle number 1, we know formula is just going to be length times width. So the length, or the height of this rectangle, we can look at that left endpoint. So the left endpoint of that first rectangle is right here. It starts at 0, it goes up to where it meets the curve here. Where does it meet the curve? At x0. So my height is going to be the value of the function at x naught, at that left endpoint. Well, what is going to be the width of this rectangle? Well, we know it goes from x naught over to x1, so let's just call the distance between our two x values here, we're going to call that delta x for the change in x, or the width of each one of our little rectangles here. So the area of our first one is f at x naught times delta x. We can make the same sort of argument for our next rectangle. It's going to be, well, let's see, the height is from here to here, okay, where this from 0 to where it meets the curve y equals x, so it's going to be f at x1, because it's at x1 that it meets the curve, times delta x. Similarly, for our next two rectangles, A3 and A4, we're going to have f at x2 times delta x, f at x3 times delta x. So what's our area going to be? Well, we can just say that our total area under our curve is going to equal the sum from 1 to n of our function evaluated at, let's see, what's our pattern here? We go 0, 1, 2, 3. So if I starts at 1, we've got to do I minus 1 times delta x. So there's sort of a general formula for finding the area under the curve using left endpoint rectangles here. Now, we didn't have to set up our rectangles exactly that way. We could have done what are called right endpoint rectangles. In which case, we're going to take our same region here from x naught, x1, x2, x3, all the way up to x4. So the area from x naught to x4. But instead of putting the left endpoint of each rectangle on the curve, we're going to draw we're going to draw our rectangle so that the right side of each of our rectangles intersects that curve. So again, we're having 4 rectangles, 1, 2, 3, 4. Okay. These are sometimes called circumscribed rectangles because they cross f at x across the curve, rather than the tops of them cut across the curve rather than being completely contained underneath it. Well, we can do the same thing that we did before. Again, our function here is still y squared. We can look at the area of each one of these sections. Area 1 is going to be the width, delta x. We'll still define delta x the same way we did before. Okay. And what is the height of our rectangle? Well, the height of our first rectangle now, it meets, the height is going to be this distance sort of right here like this. That is the value of the function at x1. So this is going to be f at x1 times delta x. Similarly, for our area 2, it's going to be f at x2 times delta x. Area 3, f at x3 times delta x. And area 4 is going to be f at x4 times delta x. So if we put all of this together, we can say that our total area is going to be the sum as I goes from 1 to 4 again, of f evaluated at x I times delta x. Now, if we compare these two methods, what you can see in this first method here is that we've got a bunch of blank space underneath our curve that we're probably not considering when we do our and our sum. For instance, this little region in here, and in here, and in here is area that is underneath the curve but not part of our rectangles. So this method is likely an underestimate of the true area in this case. And there's an E in true. If we compare it to this method, well, we've got a bunch of space that is in our rectangles, but should not be counted as part of the area underneath our curve. So in this case, this expression here is likely an overestimate of the true area. Now, is there a way that we could do this to sort of balance out this overestimate and this underestimate? Well, what we could do is, there's another way of doing this. Okay, and I'm just going to pause the video here. As I was saying, there's another method that we could use. And in this case, rather than drawing, first one we had left endpoint rectangles, the second one we had right endpoint. This time we are going to draw what are called midpoint rectangles. So we still want to cover the same sort of range underneath the curve as we were doing before. So we still want to have x0, x1, x2, x3, and x4 here. But when we draw our rectangles, we're going to take the middle of each little range. I'm going to draw a rectangle so that the midpoint of that rectangle is right on our curve f at x. So again, we're going to come up here, and we're going to draw something that kind of looks like this. And something that kind of looks like, that one wasn't all that good. And this one will kind of go like this. So right in the middle of each of these rectangles is where it crosses the curve. So if we do this, then sort of this little area under the curve here, and this that is not in our rectangle, but we should count, and this little area over here, which is above our curve and inside our rectangle, will sort of cancel each other out, and we'll get a much better estimate for the area. So let's figure out the area for each one of our little rectangles again. Again, it's going to be length, or sorry, the width times the height. For the height, we're still going to use delta x. What about for the height? Well, for the height, we still want to find a value of the function, but where do we want to find the value of the function? For our first rectangle here, we want to find the value of the function at a point that is halfway between x0 and x1. So it's going to be f evaluated at x0 plus x1 all over x2 times delta x. Same thing for area 2. We're going to evaluate the function at the average of x1 and x2 and multiply by the width. And we can continue on in this way for our next two rectangles. x3 plus x4, take the average, and multiply by x. So if we put this together into a final expression here, our total area is going to be the sum, as I equals 1 to 4, of f at x. Let's see. So for our first box, I is 1, but we want x0, so we want x, I minus 1, plus xi divided by 2 times delta x. So those are three sort of summation formulas that you could use to estimate the area underneath of a curve. So let's take a look at an example here. Estimate under the area under the curve f at x equals negative x squared plus 16 from x equals 0 to x equals 4 using 4 intervals and a left endpoint approximation. Then we're asked the question, is this an overestimate or an underestimate? And an underestimate right there. So let's sketch a little graph here of what this thing is going to look like. We've got x, we've got y. Our function is going to be an inverted parabola coming down like this. Vertex is at 16, and 4 in this question is actually the x-intercept of this. So we want to divide this interval. We're going to go from x equals 0 to x equals 4, so we can sort of go 1, 2, 3, 4. We've got our 4 intervals, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. We want to use a left endpoint approximation. So we want to draw these things so that the left side of each rectangle is right on our curve. So our first rectangle is going to go from 0 to 1. The left end of it should be right on the curve. So we're going to draw a rectangle like this. Our next one goes from 1 to 2. The left endpoint has to be on the curve. Same thing with our third one. And same thing with our fourth one. Okay? Each of these, left side of the rectangle is right on the curve. 1, 2, 3, 4. So we want to use our left endpoint approximation. The formula that we had on the first slide was, this was the sum as I equals 1 to 4. Okay, we can use it exactly the same way. F at x to the I minus 1 all times delta x. So what do we need to put in here? Well, we need to put in f at x is going to be negative x squared plus 16. Our delta x in each case is going to be 1, okay? Or we can think of it as we're going from 4 to 0, okay? From x equals 0 to 4. So we're going from 0 to 4, so we want to do our entire range here, 4 minus 0, and we wanted to use 4 intervals. So delta x has to be the entire range divided by the number of intervals. Each one is just going to be 1. Now, how are we going to do this sum? Well, I would say just break it up and do it area by area. Okay. A1 is going to be f at 0 times 1. What is f at 0? Well, we sub that in. We get 16 times 1 equals 16. Area 2, and this is basically just calculator skills. Okay, A2 is going to be f at 1 times 1. What is f at 1? Let's see, negative 1 plus 16, so that's going to be 15 times 1 equals 15. And we can keep on going for our next 2 intervals here. A3 is going to be f at 2 times 1. F at 2 is going to be 12. 12 times 1 is just 12. A4 is going to be f at 3 times 1, f at 3 is going to be 7 times 1, so that's just going to be 7. Okay? So to get our total, we just add up all of these numbers. It's going to be 50. Now the final thing that we're asked here, is this likely to be an overestimate or an underestimate? Well, if we look at our graph, we can see that when we drew each of our rectangles, we had a fair bit of area here that it is in our rectangles, but should not be under our, is not under our curves. So it looks like what we've got here is we've got an overestimate, that our rectangles are too big. So we can just sort of say this is an overestimate.